Yeah, hi. Am I audible? Can you please respond?
Yes, it's audible.
Yeah, okay. So we will wait for 2 or 3 minutes more, then we will start the session. Let's see if anyone else joins or not.
Okay. Okay.
Yeah. Yeah, okay, let's start. So, hello everyone, my name is Srijan Mukherjee and I'll be taking this live session for NPTEL course on Operating System Fundamentals. I'm a research scholar at the Department of Computer Science Engineering, IIT Kharagpur. So, in this session, we'll be discussing the contents which was taught in week 10, as well as we'll be solving some problems related to it, some sample questions. So, let's start this session. So, uh, for week 10, let's just do a recap of last week. That will help. So, previously, we came across this term called page and frame, right? So, so the first problem why we are using that, like, so what was basically a page? So basically we are breaking up the process, breaking up the process into smaller parts, right? So why is it, was it required to break up the page? So simple was memory management, right? So what was the problem? So our memory have different segments or partitions. So the partitions can be same, may be having same amount, same size or variable size, but the problem was in accommodating uh, the process. So the process out of various size, we saw that as a result of like the problems that was relating to memory management, what we found was that if you are uh, putting the process into correct partitions, then it is fine. There is no zero or minimal wastage of memory. But if you are trying to put a 4 KB process into a 10 KB slot, that means you are wasting 6 KB of memory. So as a result, we found out that dividing the process into smaller parts is a much more welcome step. So uh, so we come to the part called page. So each program is, or the process is broken into smaller parts. The smaller parts occupy small partition of memory space called frames. So on one side, on the program side, you have something called pages. On the physical side, physical memory side, you have something called frames. But we also find out that page size is equal to frame size. So size of page is equal to size of frame, right? After that, we also came across like these terms called physical address and logical address. So what we found out, for CPU knows logical address, whereas physical address is the address present in the memory, the original address. Right, so here you have your physical address, and this side, in the CPU side, you have your logical address. So we also came across the term that how we are getting the logical addresses, like when you are running a program, so you have this thing called array index 0 to 127. Then it's get converted to array index 0000, 0004, 0008, right? Similarly, ultimately, this is your logical address for each array element, and then you are using an MMA to translate this logical address to main memory address, which may be 7014, 7018 correspondingly. So MMA was doing this address translation, main memory translation, address translation from from logical address to physical address, right? So each page has a logical address and each frame has a physical address. So we also find out each process each process has a unique data structure called page table. So what was this page table? So in a page table, what we have is the page number and the corresponding frame number where it is stored. So here if you have a physical memory, so this frame can be one of any one of the content, and this page number will be any one of the page. So this page table are used by the CPU to locate the correct location where these pages are stored in the main memory. That is basically the frame. So this part was done in last class, and we are looking at the way to, so we also looked at the way to how this is stored. So what we had, so how the addressing is done we also saw. So you have, so if this is a n-bit address, and this is the size. Sorry, let me just redo it. So this physical address will be something like this. So this will be the offset, and this will be the frame number. So what this offset will decide? So this offset will decide what is the size of the frame. And then you have your frame number equivalent to all of it. Okay. So uh, your similarly for your page you will have your offset. So for your, this is your physical address, and this is your logical address of one page. So you have your page number and the offset. So basically the offset remains same, that is the size of the page or size of the frame. Only this page number to frame number translation is done by your page table, right? So these are the things which we went through in last slide session. So if you have any doubt regarding this page, you can ask. I will be happy to help. So any doubt you can ask regarding paging. Then we will move on to the advanced topics of this week and virtual memory.
So can you please give one example regarding this,
Regarding what?
regarding page number and offset, where there's a numerical on this concept?
Yeah, okay. So let me open the slide, okay? The slide has some example. Give me a minute. Yeah, so let me come to this one. Okay. Let me just clean this up. This I did last week. Yeah. So this is your. So we will look into the address translation. How the address translation is happening. So this is an example of your address translation. So as I said, so for CPU you have your logical address, but CPU doesn't know your physical address. So what is the address here? So what we'll do is it will consult the page table. So this is your physical logical address, and this is your physical address. This is your frame, and this is your basically there will be a page for each program, each process. So also remember, each process will have its own page table. Okay, so the process is, so this and this remain same, and the reason is that d basically is the offset. So basically it represents this size. So what is the size of frame slash page? Okay, so if you look at this slide, This will give you a better example what I am telling. So it says you have a logical address space of 2M. So you can consider this as a like, suppose you have been told that you have a memory of 2 KB. That is what this means. Okay, so it has a logical address space of 2M. So what does logical address space mean? Logical address space is basically referring to the total total size of process. Okay, so when you are given a sum to do it, so this is how you will solve it. So you have been given a, so this is the total size of the process. Now you know the process is divided into, process is divided into page, right? And now we know each page has a size 2 to the power n, right? So how many number of pages? So you have a total size of 2 to the power of m, and size of each page is 2 to the power of n. So total number of pages is basically 2 to the power of m minus n, right? Right. So your your page table, that is your page table, will have how many entries? So these are the total number of pages. So what does the page table contain? Page table contain of, for each page, the corresponding frame where it is stored. So size of the page table will be 2 to the power of m minus 1. It will contain this amount of entries. Now to represent each entry, how many bits are required? Simple, m minus n. So our logical address space will have a page number that will occupy m minus n bits, and n, that is your size, that's basically your offset. So how will you, what do I mean when I say an offset? So when I am given, so address space like 10146, let's say 2. So suppose this is the page number and this is the offset. So what does it mean is, go to the frame 4014, suppose this is the frame 4014, and go to this address line. So let's say it starts from 0 1 2 dot dot dot. So you go and find this page, so this 62th element. So if this is the total frame, so its job is to find out this. So this is what it is doing. So now you have any doubt, you can ask.
It's clear.
It's clear. So one thing is, whenever you are giving any competitive exams like GATE and all, these paging questions will be like very frequently asked. So you will be given a this like size of the physical address, size of the logical address. You have to be found out what is the size of the page table, how many entries are there in the page table. So these are the type of questions which are very commonly asked at GATE. Okay, so let's come, so this paging hardware is okay. So let's come to, so okay, so this one was done last week. So let's come to this week's class. Okay. So first we start with allocating frames to a new process. It's basically same. So when a process comes, it comes with its pages. So the pages get stored randomly after allocation to some location, and the page table is then populated, like, okay, So this is the frame where it goes. So suppose page 1 is in frame 13, page 0 is in 14, page 2 in 18, and page 20 in 3, page 3 in 20. Okay, so these allocations, so how does this allocation happens in the frame? So we went it through last week. We went through the algorithms: best fit, first come first serve. Yeah, so these are the different algorithms that are there, which determines how the frame gets populated, the physical memory gets populated when a new process is arrives. So now let's come to this thing called TLB, right? So before going to that, let's come back to this diagram. Let's come back to this diagram. So how many memory access are happening here? How many memory access to fetch a frame? So you have one memory access and two memory access, right? So you require basically two memory accesses to fetch a frame from the main memory. Now you don't, so as you know, fetching something from main memory is costly. So main memory is slow, right? So for faster access, what we'll have is something called this translation look ahead buffer, or TLB. So what does this TLB have? So TLB will have a list of frames, a page, and the corresponding frame number. Okay, so what will happen is something like this, right? So you will have your uh, if you have your, if you have this, so if it is a TLB hit, you can directly get the frame number from here and get the physical address. Whereas if it's a miss, what will happen is this procedure. You have to go through this line, which is a slower line. Which is basically a slower line. So let me explain it again. Uh, so instead of two memory access, so now we have a fast memory access with TLB, as well as a memory access. So in this path, you are doing two memory accesses, because page table is also present in main memory, and this frame is also present in main memory. Here you are doing basically a TLB plus main memory, if you are following this path. So why this? So why you need a TLB? So notice this page table actually is present in the main memory, whereas this TLB is some sort of a faster memory, like cache, which is associated with the CPU. So if the CPU gets a TLB hit, it can directly go via this route and do it, and it will require only one memory access, one slow memory access, whereas this will require two slow memory accesses. So what I mean to say is TLB plus this time is basically less than twice this you need to understand. So here what we are doing is we are hitting a TLB and then doing the memory access, whereas we are doing the two memory access. So the concept is basically TLB plus is less than into 2. So that's the reason you need a translation look ahead buffer. So that's what is done. So basically it's doing the same. P is basically if an associated register, then get the frame number out, otherwise frame number from the page table in the memory. So TLB is typically small, so it has only this much amount of entries. On a TLB miss, the value of the value of the missed page table frame number is loaded into the TLB for faster access, and that the address is used. So some TLB stored address specific unit and this. So what this means is, so this means something like this. Uh, so So you have something like this, that this TLB is basically very proximately closed to your CPU and it is fast. So what we have said here is done. So how do you populate this TLB? So what happens is, suppose initially the TLB is empty. Suppose initially the TLB empty. So basically it will always be TLB miss in that case, right? It will always be TLB miss in that case because it is not present in TLB is empty. So when our TLB miss happens, so what is done is that for the page number there is a TLB miss, it picks that up, it picks a chunk of that memory up and it stores here, it gets stored here. So next time if p plus 1 comes, it can find the it in the memory in this TLB. So when next time when the CPU fetches p plus 1, so initially there was p and TLB empty. When p plus 1 now is requested, it is present in the TLB and it will go through the faster path. Okay, so that is how you populate the TLB. So any doubt regarding TLB? Any doubt you can ask. So TLB is very close to what you have in cache. So it's very close to how cache works. So you can call it a cache for the pages. Okay, so let's move on. So now we'll calculate what is the effective access time. So let's say the TLB hit ratio is alpha and the associative lookup time is this theta. So if it is a TLB hit, so you require one memory access plus theta, whereas if it is a TLB miss, you require two memory access plus eta. So the effective time is basically 2 plus eta minus a. So this is your equation for calculating the effective access time when TLB is present. So here is an example given. So suppose E is equal to 20 nanoseconds for TLB search and 100 nanoseconds for memory access. So if eta is 80%, the heat alpha, the heat rate is 80%, then it is basically 0.8 into 100 when there is memory access, plus 0.2 into 200 when there is so this is for memory access, and this is for like the miss, because this is the hit rate. So in case of hit rate, it has only 100. So it is basically wrong. It will be 100 plus 20, and it will be 100 plus 100 plus 20, right? So a more realistic heat ratio is alpha is equal to 99%, because a cache, the primary concern for your cache is that is for faster access. So in most modern systems, cache needs to work better way for faster access and memory. So that is a realistic aim, that alpha is equals to 99%. Now let's talk about memory protection. So memory protection is basically implemented by associating an extra protection bit, which each frame is indicated as read only or write only access. So also for each page table there is a valid and invalid bit. So valid bit indicates that associated memory page is within the process logical address and is thus a legal page. Invalid indicates that the page is not in the process's logical address space. So it's something like this. So this is your frame number, and this is your valid bit, and this is your page. Now since there are 6 pages, and you see 6 pages are located in particular memory places, so you have these 0, 1, 2, 3, 4, 5, 6, 5, all of them are valid because they are present with the program. While the rest 2, 6 and 7 are basically invalid, so they are not associated with the program as well as they are not present in your main memory. So this is how your valid invalid bits helps in maintaining the authority of your data or your process. So any doubt regarding this? So shared pages. So one copy of read-only code shared among many processes. This is a very common logic that has been implemented for real life, like your text editor. So suppose you are using Microsoft Word. So some part of your so you have opened 2 files, right? So some part of the code in which Microsoft Word is written can be shared between both of them. For example, the process of highlighting a text, like changing the color of the text, so that code should be same for all the processes, right? So why can't you use that code? Both of them can share the same process, the same page. So that is basically your concept of share page happens. So you have your private data private code and data. So each process keeps a separate copy of code and data as well. The pages for private code and data can appear anywhere in the logical address space. So each process also have a private code on data. So and they can appear anywhere in the logical address space, but those are private code. This is your shared page example. So you have your process P1. This is your page table for P1, process P2, page table for P3, P2, P2. So as you can see, all of them share the same page, right? P1, ED1, E2, ED3, and data 1, ED2, ED2, ED1, ED2, ED3, and data 3. So you notice data 1 has a different page number, data 3 has a different page number, and data 2 also has different page number, but rest are same. So that is basically you are sharing it. So while the data part is same, so if you have an MS Word code, MS Word, and opened two files, then code for increasing text size is independent of the process, but the files are different, meaning different data, right? So as you can see, the data has different page numbers, but your shared pages have same page number. So any doubt regarding this? So any doubt you can ask. So now let's consider the structure of a page table. So you have a 32-bit logical address space. You have a page size of 1 KB. So you have a 32-bit logical address space and the page size is 1 KB. So number of pages is basically 2 to the power 32 minus this 2 to the power of 10. So this is basically 2 to the power of 22. So page table will have 2 to the power of 22 entries. Now each entry is basically the page table will have 2 to the power 22 entries. Now also said that each entry is of 4 bytes. So page table is of size 2 to the power 16. So basically you will do is 2 to the power of 22 into 4 bytes. So this will approximately come out to be 16 MB. So as you can see, if a process has 32-bit logical address space and a page size of this page table as this, so each process will require 16 MB page table. Process will require 16 MB page table. So what will happen if you use a 64-bit logical address space? So previously it was 32-bit logical address space. What will happen if you are using 64-bit logical address space? What will happen? So the immediate impact will be, so now you are maintaining for each process a page table of 16 MB, it will basically rise. It will basically rise. So it will be approximately 4 times. So what we are seeing is, if you have a larger logical address space, the size of page table for each process goes up. So this is not a good solution. So page table, you can see that as the size increases, it will basically cause a problem. So now you are dealing with only 32-bit logical address space or 64-bit logical address space, but very soon it will just go beyond it. So 16 MB is too much in that case. Now it can be seen as a small, but after that it will be a very big problem. So one thing is done to do this. There are quite a few techniques to overcome this. So page table for large address space, for large address page table for large address space can be done in this type of types: hierarchical paging, hashed paging, inverted page table. So we'll go through them one by one. So let's have a brief overview what we mean by hierarchical paging. So in basically hierarchical paging, there is not only one page table. So there are more than one page table, and it basically forms some kind of tree structure. So this is an example of a 3-layer hierarchical paging. So here each entry will point to another hash table. Similarly, these entries here, each entry will point to another hash table. Each entry will point to another hash table in another page table. This also in another page table. This is also in another page table. So that is your way of hierarchical paging. So as you will see later, this reduces the size of the page table we need to maintain in the memory drastically. So this is the example of your hierarchical paging. So break up the logical address space into multiple page tables, not breaking up the single address space into multiple address spaces to multiple page tables. A simple technique is a two-level page table. So this is a two-level page table. So this is an example of a two-level paging. So what you have is basically a 32-bit machine, and it is divided into a page number consisting of 22 bits and an offset of 10 bits. So if you are using a single page table, so you will have this 22-bit and 10-bit. So what we will do is, for two-level paging, we'll divide it into this. 12-bit page number and the 12-bit page offset. So so uh, so while previously D was your frame offset, now you have your two offsets. So this is for page table 1, this is for page table 2, and this is for frame. So P1 is the index to the outer page table, P2 is the displacement within the page of the inner page table. So this, it will be something like this. So you will have your outer page table. From there you will pick up the next level page table P2, and there you will pick up the location in the main memory. So this is your translation scheme in two level page table. So any doubt regarding two level page table, you can ask. So let's come back to this. So you have a 64-bit logical address space. You have a two levels paging scheme. Each page size is 4 KB. So basically your offset is 12. So then the page table will have, if you are using a one level paging, then you have two to the power of 52 entries here. So how is it? Basically 2 to the power of 64 divided by 2 to the power of 12. That is basically 2 to the power of 54. Okay, so now let's say you have this scheme. So by if two level scheme, the inner page table should be 2 to the have 2 to the power of 10 4 bytes entry. So it becomes like this. Inner page will be 10. There will be 10 small inner pages will have 10 entries each, and then you have your outer page. So the outer page table will have 2 to the power of 42 entries or 2 to the power of 44 bytes. So again the size is high. What you can do is further divide it. So this is a 3 level page table. So you will outer page will have 10, 10, 32 and an offset. Similarly you can again go for 4 level, where it will be something like this: 22, 10, 10, 10 and 12. That is how you can go on and on to break the page table. So if you notice, the size will decrease when you are creating much smaller page tables, right? So here you will have only small page tables of size 2 to the power of 10, 2 to the power of 10 and 2 to the power of 32 compared to a total whole 2 to the power of 52. That is quite less. Now there are other methodologies also. So this is still a very complex way, and it still requires a lot of memory. So let's come to another concepts. So there is hashed page table and inverted page table. So hashed page table, what happens is, so you have a page number hashed to a particular page table location. So it will be something like this. So you have your logical address space, you will have a hash function. Hash table will contain all the corresponding physical addresses page here, and you can just refer it via this to physical address. So instead of storing multiple tables, you will have basically a linked list here. So each element contains a virtual page number, value of the mapped page frame, and a pointer to the next element. So this is basically your pointer to the next element. This is your mapped frame. This is your mapped frame. And this is your page number. So instead of having a table, we'll have a single table, hash table, where here for a particular entry hashed there are a linked list situated, and you basically traverse this linked list to find appropriate your appropriate frame, right? So that is how your uh, hashed frame page table works. Okay, so this is not much important. So your main important is basically your main page table, which whether it is efficient or not, it is still a very popular one. Okay, so this is your page number, this is your mapped frame, and this is the linked list to the next one in the hash for that logical address. Okay, so any doubt regarding hash table so far? Okay, so let's go to the next slide. So now you will be allocated the introduced to the concept of an inverted page table. Okay, so let's come to this slide. So far so good. What you have a page table for each process, right? So it can be one so the page so page table for each process, so it can be one layer, two layered, or multi-layered, anything. So what was that? So in the page table was basically what we are doing for each page number. So each page number you have a corresponding frame number, right? So this is the procedure, page to frame mapping. What if we do the opposite? So you have list of frames, and for each frame you will have your process ID and page number, right? So so what so what like what gain we are making if we do like this? So this is basically the opposite mapping. Instead of the forward mapping, we are basically the backward mapping. So what gain what we are making out of this? So the basically uh, logical address space So these are for each processor table. We saw it is very large in total if there are many processes. But when we come to this, what we'll have is that for each frame there is a table entry. So where for each page there was a table entry, here we have each for each frame we have a table entry. So basically for each frame there is a page number, as well as to we need to identify whose page is this, which process page is this. So there will be a process ID also associated with it. So in this case what will be physical address space is equal to memory address space. So in short term this is what is happening. So your physical address space and your memory address space are fully equal in this case, whereas previously it was different. So for each process there is a table. Here there is a universal table for each frame. So each frame will be allocated to a particular page number and the process ID, right? So that is your table in this case. And the only way reason this one is preferred is because of the size. Again, the physical size and your logical size are completely same. So that is the crux of why you are using an inverted page table. So any doubt regarding inverted page table? Okay, so let's go to the next slide. So this is basically your inverted page table. You have your for logical address will basically your continual PID, your page number, as your offset. Offset goes just like that previously. And what you will search here, for which frame PID and P is present. Basically the reverse search, nothing more. It will find out the frame num ID and then the physical address is found. So that is your uh, inverted page table architecture. So this is your logical address. So PID and P will be used to search the frame got. Already we know the logical address, this offset, and we will search in the physical memory for that process, page. So that is how we end the talk on inverted page table. So the advantage is basically decrease memory needed to store individual page table, but increase the time needed to search the inverted page table when a page reference count occurs. Okay, so it reduces the memory, but it increases the size to require the to scan the inverted page table. So you can also use hash table to limit the search to 1. Okay, so we will come to virtual memory later. We will revisit this when we encounter it later. So now these are some case studies like how Oracle Spark Solaris uh, OS does in for paging and other stuffs. So it is based on hashing but not complex. So you can go through this at your own convenience later. So these are basically case studies. You can go through it. Same. So say then there is the Intel architecture example. This is a way for logical address translation in IA32. This is Intel's paging architecture. Okay, so with that we end paging, page table, inverted page table, and etc. So please let me know if you have any doubt. Okay, so let's continue to the new concept which will be introduced today, that is virtual memory. So so one thing we saw is paging is done for memory management as well for allocation superiority, right? So this is the reason paging is done. Now as you saw, uh, when the program slash process is divided into smaller parts, what happens is you don't need all the pages all the time in memory, right? So consider the situation where you have so suppose let's go back to the word example. So you are changing the color of your text, right? You are changing the size of your text, but do you need to have the so that is done by some page, right? So that changing the uh, data like for changing the text color or size, that some page is doing it. But at that point of time, do you need a page which copies a file like word? So you can go to the file and do a copy of this file or print the file. Do you need that page at that point of time? The answer is no, you don't need it, because you are not doing that task. You are doing editing of the document task, but you are not doing the read and write of the task, right? So that is one example that you don't always need the page in your main memory during execution, because as you know, your uh, main memory uh, faster, and that's why it's a much more costly. So your main memory, like your like your RAM, So you, in your machines, you have your 16 GB of RAM, 8 GB of RAM, but you have a hard disk of 1 TB, because hard disk is cheap and RAM is faster, so it is much more costly. Now you are being told that all the process, if you run all the process on your RAM, which is very limited, 16 GB compared to your 1 TB of hard disk, you will say that okay, so that is not correct, right? So your program may crash. You don't need all the pages all the time. So in that case, your concept of virtual memory arrives. So what happens in case of virtual memory? The process, CPU considered a process uh, can exist out of your main memory also into secondary memory, and it is transferred from secondary memory to main memory only when your process needs it. Otherwise, it doesn't get transformed. So your, for your word example, that read write to a printer will only be taken into the main memory only when someone evokes it, someone needs it. If it is not needed, go back to your secondary memory. So that is the concept of your virtual memory, where the CPU thinks you have a large uh, memory, but actually you have a very small memory. So let's say the CPU thinks that you have a 300 GB of RAM because your hard disk is 1000 GB, but in reality it only has 16 GB of RAM because that's what it is packed with. That cannot be extended. So the way of handling this is basically the virtual memory, which we are talking concept of, which the concept we are talking. So let's share my slides again. As I said, code needs to be in memory to execute, but entire program is rarely used. Error code, unusual routines, large data structure. So entire program is code are not needed all the time. Consider the availability to execute partially loaded program. Program no longer get considered by the requirement of physical memory. Each program takes less memory while running, hence more programs get executed. Less I/O needed to load or swap programs into the memory, hence the user runs faster. Okay, so these are some exciting points, important points regarding the uh, like some of the features of your paging, why it is used, why, when not to use, etc. So any doubt regarding your virtual memory so far? You can ask if you have any doubt regarding virtual memory so far. Okay, so let's go to the next slide since you are not having doubt. So virtual memory is basically a separation of your logical memory from physical memory. Only a part of the program needs to be in the memory of for execution. Logical address space can therefore be larger than your physical address space. So your logical address space is basically greater than your physical address space. So it allows for more efficient process creation. So since you don't require all the pieces of your process at the same time, you can create much more processes. More programs can run concurrently. Less I/O needed to swap or load processes. So virtual memory can be implemented via demand paging or demand segmentation. So we'll come to these demand paging terms one. So this is your virtual memory. This is your memory map, or maybe you consider it as your typical page table, and this is your basically physical memory, and this is your basically secondary memory. So few parts of this physical memory get transferred here, of the from the secondary was transferred here, and rest remains here and only gets transferred when required, right? So that is your virtual memory concept. So now let's come to this. So you have your virtual address space. So this is your heap basically. So usually the design logical address space stack for stack as it start magically going up and grow down when heap grows up. So either this goes up or this goes up. So this is the direction in which. So unused address space is the hole between the two. Maximum address use space. No physical memory needed until heap or stack grows to a given page. So no physical memory is needed. You do as many of your alloc, malloc, calloc. Enable address space parse with holes left for growth. System libraries shared via mapping into a virtual address space, and then your shared memory by mapping page read into a virtual address space. Pages can be shared during fork, speeding the process creation process. So these are some terms which you will require for virtual address space. So just remember one thing: for a process or a CPU running the process, it doesn't care about physical memory. It only deals in virtual memory. It has list of logical address and works with it, does not bother about main memory. So this works seamlessly in such a way that your CPU doesn't have to understand, okay, where is my page and all. So it just does its job as it is required. And there are tools like the page table or memory management, translation and all. Those takes care of this conversion of virtual memory to physical memory and all. Okay, it doesn't care about also whether it is present in your the pages are present in your main memory or secondary memory, right? And how why it have to maintain it. This is the level of abstraction it requires. Otherwise every time it has to stop and start and think about, okay, now I don't have memory, now I have a memory, right? So CPU needs that flexibility to work at high speed and all. So it doesn't have to care where my pages are there. So it just invokes it. If the page is not present, it brings it to the main memory and works. So now let's look at the next slide. So this is your shared library, shared pages for each, uh, using a virtual memory for each of the different processes. Now we come to the concept of demand paging. Now we know, if this is your program and corresponding pages, so at first only you allocate, bring few pages into the main memory, swap in few pages in the main memory, let's say 2, 3, 4 and 6, right? CPU is working with it, no issue. Suddenly it says I need 8, right? Now, is it present in your main memory? Is 8 present in your main memory? No, right? So that is a miss. What we call it in here is called a fault. Page fault. What does page fault mean? Basically, you are trying to get your frame number 8, which is currently not present in your main memory. So that is basically what we term as a fault. So when you're trying to access it, it says, okay, this is not present. So what happens in that case? So in that case, 8 gets swapped in to the main memory from the secondary memory, right? So in that case, page 8 gets swapped in into the main memory. So that is your called demand paging. So when you require it, then only bring it, right? So there are very many algorithms for this demand paging and stuff. So one can be when to page in or page out, so first come first serve, which one to replace, which one of the frames to replace, because you have only a uh, limited frames, whereas you have a large amount of your pages. So there are many different algorithms based on it, like last used first, those kind of things, paging, round robin, first in first serve, round robin, those kind of many concepts are there, which take care of this phenomena of bringing a page into the main memory, and which one has to be swapped out of the main memory in its place. That there are many algorithms. We'll discuss it in future classes. But for the time being, you have to understand what is demand paging. So demand paging is basically for swapping in a page from your physical memory to your main memory only when you require it. Else you don't do it. Okay, so any doubt regarding demand paging so far? Okay, so let's get on with it. So this is similar to your paging system. So page is needed, reference to it, invalid reference, abort, not in memory, bring into the memory. So swapper deals with pages is called a pager. So basically a swapper which swaps it in out and all is called basically a pager. So when a process used to be is to be swapped in, the pager guesses which page will be used before the process is swapped out again. Instead of swapping in a whole process, The pager brings only those guessed pages into the memory unit. Need MMU functionality to implement demand paging. Need to distinguish between the pages that are in memory and pages that are on the disk. So we use that valid invalid scheme for this. If pages need are already memory resident, then there is no need for demand paging. If the page is needed and not in memory, then you need to detect and load the page into the memory from storage, right? So what we said previously, that if it is not in the memory, swapper swaps it in, uh, and this is in one of the few empty frames. If there is no frame empty, it swaps one page out of that frame and puts it there. So there are algorithms to deal with it. Not, it is not random. Either it has first come first serve or least recently used algorithm or a round robin one. Okay. So how do you know whether a page is present in the is present in the memory or not? So you again have that page table with a valid invalid bit. So the frame number, so you will have the frame number and the corresponding valid invalid bit. If the bit is invalid, that means not present in main memory. If it is valid, that means present in main memory. That is nothing more. That is what it means. So during MMU address translation, if valid, so during MMU translation, if a valid bit in the page, valid invalid bit in the page is I, that means it is a page fault. So when there is a page fault, swapper swaps swapper slash pager swaps the page into the main memory. Okay, so that is what happens. So here is the concept. Let's say, see your page table in your physical memory. Page A, C, and F are present in frame 4, 6, and 9. So these are valid. In location 4, 6, and 9. But see, others are not present. So you see others are not present, like B is not present. B is not present, which is basically your page 0 is not present. So you see this one is invalid. 3, that is D is not present. D is present here, D is not present here. So again it is a invalid bit. So that is how you do it. The pager sets the valid invalid bit okay. So any doubt regarding paging? So let's so page fault, as we discussed, if there is a reference to the page, first reference to the page will trap into the operating system page fault. So page fault occurs when a page requested is not in main memory. That is your page fault. So actions: when a page fault occurs, operating system looks at another table to decide valid reference about not in memory. Go to step 2, finds a free frame, swap the page into the frame via disk check operation, resets the table to indicate that page now in memory, set the validation bit to V, restart the instruction that caused the page fault. Right. So these are simple steps. So find the free frame, swap the page into the frame via scheduled disk operation, and reset the table to indicate the page now in the memory, set validation bit is equals to V, restart the instruction that caused the page fault. Okay. So any doubt regarding this, you can ask. So we are almost at the so these are the steps of that we discussed of handling a page fault. So this is search for the reference. Page fault occurs. Page is on the main memory. Bring the from main memory to a free frame that is in the in the physical memory, and then you reset the table and make it V. That is all happens when there is a page fault. Aspects of demand paging. Pure demand paging. So what is pure demand paging? Start the process with no pages in memory. OS sets instruction pointer to the first instruction of the process, page fault. So in pure demand paging, your process start with no pages in the memory. So as a result, every time a page is required, a fault will be there, and so on. Hardware support is required for the demand paging. Page table with valid invalid bit, a secondary memory, that is the swap div space, and your instruction reset. So instruction reset block, consider the instruction that could access different location, block that move, page fault during the move, restart the whole process. So this is your entire steps in demand paging, how to do it, which we discussed, and continue. So if you have any doubt regarding demand paging, you can ask now, or any doubt whatever we are discussed so far, you can ask. Next we will go to the some problems which we will discuss for this week. Okay, so let's start with solving some questions. So in the first question, what we have is, we have been given a paging hardware with TLB, the entire page table, and all the pages are in the physical memory. It takes 10 milliseconds to search the TLB and 60 milliseconds to access the physical memory. If the hit ratio is 0.6, the effective memory access time. we need to find out. So what it says is that here is your CPU, it has a TLB, and a page table, and here is your physical memory. So it sets 10 seconds to search the TLB. So what happens if you search the TLB? So if you have so the heat ratio is 0.6. So if you search the TLB, it takes 10 milliseconds if it is a hit, and 80 to fetch it from the main memory, right? Whereas in the other side, for a TLB search is 10 when there is a TLB miss, plus 80 for the page table, plus 80 for the main memory access time the frame. Okay, so the total time in case of a miss, in case of a hit, is basically 90. TLB miss is basically 170. Okay, so now you are given the heat ratio is 0.6. So 0.6 times it hits the TLB hit is a TLB hit, that means 90, and 0.4 times it is a TLB miss, that is 170. Okay, so we need to calculate this. So this will be basically 54 plus 68, that is basically 122. So the correct answer is option B, 122. So what is happening basically? So the question says that if there is a TLB hit, so it will take 10 seconds, and 80 milliseconds is required to access the main memory. So if it is a TLB hit, so it will access the TLB first and then the main memory only once to fetch the frame. Whereas if it is a TLB miss, it will also not only search the TLB for 10 nanoseconds, 10 milliseconds, but it will also search the uh, page table which is actually present in your main memory. Page table is also in main memory, and then you will search the main memory for this frame. So it will also take it will also require a memory access. So two memory accesses during TLB miss, whereas a TLB hit, it is a one memory access. So the total time required is basically 122 milliseconds. Okay, so that is the correct answer. And also it was given that TLB hit miss ratio is 0.6. So any doubt regarding this question you can ask. So let's come to the next question. So the ability to execute partially loaded program enables a consumption of less memory by each program while running, b requirement of less IO for loading and swapping programs into the memory, c to run more programs at the same time or better CPU utilization. So let's look at each of the statement one by one. So if you are partially loaded, if you are if so it says that you have a program slash process and you are loading only some of it at a time in main memory. So option A says consumption of less memory by each program while running. Technically it is true because each program P1, P2 and P3 will be using less pages at any single given time, right? So as a result it will obviously consume less memory. Each program will basically consume less memory while running. So option A is true. Requirement of less IO for loading swapping programs into the main memory. So will it require less IO for loading and swapping programs into the main memory? Will it require less IO to for IO for uh, loading and swapping programs into the main memory? Yes, it is true because each time you are doing partial swapping partial. So if the IO operation while swapping 2 MB code requires 10 nanoseconds, 100 nanoseconds, IO for let's say 0.2 MB will be 10 nanoseconds, which is very small. So if this is one page, so it will basically take very less time for IO. So it will be basically faster loading and swapping program because this when you are loading or swapping this big program, it will obviously require more bandwidth and your IO will be doing some other job where like it will be stuck in just swapping the memory in and out of a huge big file that is 2 MB instead of small chunks of program like 2 MB, 0.2 MB files pages, right? So it will require less IO compared to when you are doing a bigger memory swap. Option C, to run more programs at the same time for or better CPU utilization. True. Uh, so due to this we will be able to run more programs at the same time because you require less IO, you require less memory. So obviously you can bring in more processes at the same time into the main memory, right? So it will obviously require less IO. So so all of them are correct. So the correct answer is option D, all of the above. Okay, so let's go to the next one. So which of the following is incorrect about demand paging? So in pure demand paging, process starts with no pages in the memory. Yeah, so we have discussed that in pure demand paging process starts with 0 pages and are brought in as and when required. So yes, option A is correct. Process starts with no memory, no pages in the memory. Sorry, incorrect. Sorry, it is correct. Sorry, it is very confusing, this term. Correct, incorrect. So option 1 is true. So a given instruction can access multiple pages and page fault. A given instruction can access multiple pages and page fault. Yeah, so a given instruction can access more than one pages, true, as well as it can cause a page fault, true, when the instruction is not present in the memory. So page fault can occur as well as it can access multiple pages at the same time. So this one is true. Support for page table valid invalid bit and the secondary memory like swap space are required for demand paging. True, what we have seen, a valid invalid bit is required corresponding to each frame, corresponding to each page, to realize whether they are present in the main memory or they are present in the secondary memory. So this one is true. So all of them are correct. So none of these are incorrect. Okay, so let's come to the next one. For implementing demand paging, it is required to distinguish between between the pages that are in the memory and the pages that are on the disk. It is saying for demand paging, you need to distinguish the page in the memory and the pages on the disk. Yes, we distinguish with how we have your page table with the valid invalid bit, right? So that distinguishes whether the page are in memory or in disk, right? So this is true. Use a variation of valid invalid scheme for protection too, as we discussed. Implement a new MMU functionality true. So this in this MMU is required for your paging. So when it is not present, it it goes to the main memory, it goes to the secondary memory, bring it to the main memory. Then what happens? It validates the bit and then it populates the page table and then restarts uh, your the process, the page which causes the fault, right? So all of them are correct. Okay, so the next question: virtual address space doesn't facilitate the following. Virtual address system libraries are shared by a mapping into a virtual address space. True, we saw that system libraries which are present for process P1 and process P2 are shared via virtual memory concept. So this one is true. Process creation is speeded up by sharing pages during fork. True. process creation is actually increased by, because if these two are part of the same process, then it will use the same shared library. So just share the pages among themselves. You don't have to create a new page for everything. Just share some of them because they are functionalities together and they are basically read-only functions. Next, sparse addresses are left with holes for growth. True, sparse address spaces are left with holes to grow between stack and heap. So between the stack and heap, it allows you to grow between this space. This is also true. Virtual address space does not facilitate the following. Yeah, so all of them are true. So the correct answer is none of this. Okay, so let's go to the next question. So this is that case study which is skipped. Oracle Spark Solaris use two hash tables. Which of the following is incorrectly specified about the architecture? So each hash table memory addresses maps memory addresses from virtual to physical memory. Each hash table maps a memory address from virtual to physical address. This is true because that's the task of your hash table maps, to transfer the to convert the address from virtual to physical memory. Each entry has a base address as a span. Yes, it has a base address as a span. Having a single hash table is more efficient than having two hash tables. False. More the hash tables, the more it is efficient. And each entry represents a contiguous memory area of the mapped virtual memory. Each entry represents the contiguous area of matched virtual memory. It's true. It represents it. So the incorrect one is option C. So let's come to the next one. Which of the following is incorrect about virtual memory? It allows address space to be shared by several processes. True, because it is the same secondary memory that is shared by more than one process while it is swapped out. So it allows address spaces to be shared by several processes. That is true. It can be implemented via demand paging or segmentation. True, it can be implemented by demand paging or segmentation because that's the reason you do virtual memory, like for swapping in the pages you require and swapping the out which you don't require each and every time. So physical address space is larger than the logical address space. False, because physical address space is basically your logical is less than your, sorry, so let me just rewrite it. So basically your logical address space is basically your physical address space plus your secondary memory, that is your virtual memory. So obviously clearly your logical address space is much bigger than your physical address space, right? Because it has the also takes a chunk of your secondary memory. So physical address space is larger than logical address space is basically false. It let you more programs run simultaneously. True. It allows you to run more than one program simultaneously, because you don't have to you don't need all the pages at the same time to be present in the memory for the process to be run. So the incorrect one is option C. 7 answer is C. Okay, so let's come to the next one. When a valid invalid bit is set to valid, it means the associated page is, so you have your page table, valid invalid frame, page number. Well, a valid invalid bit is said to be valid. When the valid invalid bit is said to be valid, it means the associated page is in the process's physical address space, right? Option 8. Because it doesn't, I mean, okay, it means it can be in the TLB, it can be, it has data in it, true, but the correct answer is it is in your physical address space. This is currently in your main memory, right? If it is in your main memory, doesn't it can be in your TLB, but the truth is it is in your physical address memory. It may have data, it may not have data, we don't care, but it is not in your logical address space, it is currently in your physical address space, main memory. The page is in main memory, right? So the correct answer is option D. Now let's come to question number 9. Find out the incorrect statement. So demand paging brings a page into the memory only when it is needed. True. Demand paging, as the name suggests, it's only brings a page in only when it is needed. Demand paging can bring entire process into the memory at load time. Can it bring entire process into the memory at the load time? It can. True. Demand paging requires more memory than normal paging. It requires more RAM than normal paging. True. No, it doesn't require more RAM than normal paging, because it requires less RAM. That's why you are doing it. Because in demand paging you are bringing in only few pages as and when required, whereas in normal paging you are bringing entire chunk into the memory at the same time. So that is false. So the incorrect statement in this is your option C, obviously. So demand paging, obviously the option A is correct, because it brings a new page into the memory only when it is required, and also it can bring the entire process into the memory at the load time, but it doesn't basically do it. Now let's come to question number 10. In an inverted page table, there is only one entry for each real page of the memory. Option A. Option D. So it says that for each page in the memory there is one entry. So basically it means that for each frame one entry in IPT, right? So this is true. So this one is true. It tracks all the pages rather than having a page table in each process. Again, true. It tracks all the pages instead of having a page table for each process. Consists of virtual address of the page, virtual address of the space stored in the real memory, with information about the process window. Yes, because it has the PID as well as the uh, page number, so it requires both. So this one is also true. So the correct answer is all of the above. Okay. So any doubt, any question you can ask. Okay. So that's the end of today's session. Thank you for joining. If you have any question, you can ask or you can leave. We will again meet next week. Okay. So thank you for joining. You can leave. Okay.